So, happy Monday. Exams are nearly upon us, and we're going to spend the day making sure everyone feels as comfortable and as ready as possible. Anything on your minds here at the start? Yes?
You can use the formula sheet during the test.
Yes, absolutely. Officially, you've been able to use the formula sheet on every assignment the entire semester, and it's still true of the exam. Please bring it. I will have extras even if you don't have one. Please bring your formula sheet. Also your calculator. Bless you. Your calculator that is not your cell phone. You are still allowed to write on your formula sheet. I mentioned a bunch of things throughout the semester I'd recommend putting on there. You are allowed to bring your one formula sheet that has writing on it. Like that is fine. Please bring it. It has to be designed as if you had it. Yes.
I had a question on one of the questions on the practice test.
All right.
Number 11.
All right. So here we've got motion with friction. I've answered this as if it were an energy question, but it doesn't specifically need to be done using energy calculations.
Okay, yeah, because I had initially done it like tension, like making the two T's equal each other.
Yes.
But then when I did that, I found like a different answer, so I don't know, I guess I was confused as if I was supposed to use one more than the other.
Well, I've got the energy version on my answer key. We can do a force tension version instead and see, double check that it's supposed to give the same answer. So we've got two objects. One of them is sitting on a table, the other is hung over the edge of a pulley. They are tied together, and that means that physically whatever acceleration one has, so too will the other. So each object will have some amount of net force acting on its mass, causing the same acceleration. And if we know that acceleration between both of them, we can figure out how fast they'll be moving after this one has descended a certain distance. Because if this one descends 50 centimeters, this one's going to move forward 50 centimeters, same distance, same acceleration. They should catch up to the same speed. Now for each of the two objects, they each have a different number of forces acting on them in the corresponding axes. I'm going to treat this one as object 1 and this one as object 2. So object 1 as the table object. We've got tension in the rope pulling forwards, force of friction pulling backwards, so I'll make that negative. And that needs to equal its mass times its acceleration. The second object, the hanging object, is going to have tension pulling up, its own weight pulling down. You know what, I'll put pluses in here and plug in negatives later. That's going to equal its mass times its acceleration. And note, even though they will both have the same acceleration or the same magnitude, it will point in different directions for the both of them. And so if you just leave in A for both and trust that you'll get one A with one sign on it, that's actually not going to work. And we've done this in the past. We had to manually add a negative sign to the descending object because while the accelerations have the same number between the both of them, this one points down. So we have to add that negative manually. So between these two equations, we've got two variables in common between the both of them because they both have the same rope pulling on them with the same tension, and they will accelerate at the same magnitude but different directions. We know their masses, and if we wanted to do two equations, two unknowns, we've got two equations with tension and acceleration, so they're almost at two equations, two unknowns. We just have to figure out first the force of gravity on the hanging object and the force of friction on the sliding object so that we can do two equations, two unknowns. The hanging object is just 1 kilogram. Its weight should be its mass times g. So 1 kilogram times negative 9.8. Hanging object should weigh negative 9.8 newtons. So that can go here. Then we'll also go ahead and plug in that its mass, that is a known number. So now that equation is down to the two unknowns that we want. Then for the sliding object, friction is going to be what is opposing tension. Coefficients of static and hanging friction. We know the coefficients of friction acting on it. 0.42 is static, 0.31 is kinetic. What type of friction is going to act on the sliding mass if it is sliding? Very good. Force of friction is going to equal normal force times mu. And if we're using kinetic friction, I will add the relevant k's. So, we want force of friction kinetic, we know mu k, we need something for normal force. What should the normal force acting on the 5 kilogram box be? Now the sliding box, it is accelerating left and right, but it is not accelerating up and down. So even though it is moving, the vertical axis kind of treats it as if it's not. Again, if it is accelerating to the left, it is not accelerating up or down. So the net force on box 1, the sliding box, should still be 0, and the only two forces acting vertically on the sliding box are its own weight down and normal force from the table up. If two things add up to 0, they must be equal and opposite. So if the weight of box 1, the 5 kilogram box, is negative 49, the normal force on it should be positive 49, upwards. So if we wanted to find the friction on the sliding box, 49 for the normal force, mu k, the kinetic one is specifically 0.31. So the friction on the sliding box force of the friction. I went over here to grab my calculator, and then I set down the marker that I needed. The force of friction on the sliding box should be about 15.19 newtons. And that'll be what we can plug in here. Note though that this force of friction is going to oppose the direction that tension acts on the box, so we need to add a negative sign onto it when we plug it in. And we also know the mass of this box, so let's go ahead and plug in the 5. So now we've got two equations, two unknowns, where the two unknowns are tension and acceleration. Acceleration is going to be what I'm looking for to figure this out using the tension method, because if we know the acceleration of the two objects, we can figure out the speed they get up to after they both move 50 centimeters. So, you know what? I haven't been able to use this part of the board all semester, and since there's no more tutoring announcements, I'm just going to erase it and work over here now. So these are our two equations. Let's solve for acceleration real quick. I'm going to do that by solving both of these for tension and leaving A within them. First equation, tension is going to equal 5A plus 15.9. And then for the other, tension is going to equal negative A plus 9.8. T is equal to both of these things, so now I'm just going to set the two right halves of the two equations equal to each other. 5A plus 15.19 equals negative A plus 9.8. Now we want all the A terms on one side and all the not A terms on the other. I'm going to bring this A over here. 5, no, that would act, yeah, 5a plus a is going to equal 9.8. Got to bring this term over, so the 15.19 is going to become negative. So 6a equals negative 5.39. So acceleration, the magnitude of acceleration at least, 0.898 meters per second squared. Yeah, I am not getting the same answer I did doing it the energy way. That's concerning. Well, the fact that my answer came out negative is probably the first thing that should tick me off. Oh, squared. AF squared equals the initial squared plus 2a delta y. So AF squared equals 0 plus 2 times 0.898 times 0.5. Take square root a tiny bit, not nearly enough. Yeah, I'm getting 0.95 meters per second. Using this method.
Yeah.
Sorry it took me so, I hadn't worked it the other way, so sorry it took me so long to get to that
No,
assertion.
that's fine. I was making sure that the method I was doing is correct too.
Yeah, huh. This is weird. Well, that means I need to ponder my own question and probably rewrite it. Thank you for drawing this to my attention. Now, let's instead talk about what I actually want you to be able to know and do for the exam. Because, again, the exam is finalized, so if I glance over it real quick to make sure exactly what concepts you need to be able to, that I'm wanting you to be able to use to put in better absolute terms. Things that I definitely want you to be able to do for the exam. 1, understand friction, understand how friction works. So that's why there's a friction element to this practice question. So friction, 2 types of it. Remember the 2 types, be able to distinguish between the 2. Like say in a situation like this where I give you both mu's and I tell you something's moving, you know to pick kinetic. If I tell you nothing is moving, you know to pick static. Be able to use this formula, be able to reliably find normal force to be able to use this formula. And know that friction as a force is able to do work. So I answered this like an energy question because I want you to know that friction is capable of doing work. It is capable, oh, I see. Okay. No, wait. Yeah. Friction is capable of doing work. And in this specific scenario, since the table has friction on it, it took some energy away from the boxes that it would normally have if it was frictionless instead. If the world was frictionless, the GPE of the first box would just transfer directly into kinetic energy. But in a world with friction, friction does work on the sliding box to take some energy away. And so that's how it factors into the work energy version that I did in the answer key. So remember the formulas for friction, remember that it can do work and take energy away. Furthermore, I would actually, yes. In terms of friction practice, I would also direct your attention directly to number 10 above number 11, because friction on a ramp is very interesting and very relevant. Especially note that if something is on a ramp, normal force is tilted, gravity points straight down, and friction will usually point up the ramp, either if the object is sliding down the ramp or sitting still on the ramp. If it's sitting still on the ramp, it wants to slide down the ramp, and that means friction has to point opposite the direction it wants to move in. If it is moving, then friction's still going to point opposite that motion. So static or kinetic, as long as it's not being pushed up the ramp, friction should still point itself up the ramp. Bless you. And even though normal force is tilted, because normal force always has to be perpendicular to the surface creating it, normal force is still the number you use in this formula. You just have to factor in that it's tilted while you're calculating normal force. To that end, make sure that you know, or perhaps have doodled on your formula sheet, this triangle, how these three forces relate to each other on an incline. If everything's balanced and moving normally, normal force perpendicular to the ramp, gravity straight down, and the force of friction along the ramp's surface should form a right triangle. The triangle goes as such. Basically just take the three lines that I put on the picture, drag them into a triangle shape like this. So right angle goes between normal force and friction, because friction has to be parallel to the slope and normal force has to be perpendicular to it. Gravity always points straight down. So the right angle always goes between normal force and friction, and the angle of the slope itself is the angle between normal force and gravity. So whatever the theta of the incline is, it goes here on this rearranged force triangle. So as it relates to the friction part of the exam, I focus mostly on this example. Again, do note how the incline changes the relationship between gravity and normal force. I would again recommend having this on your formula sheet. Looking back at number 11, the other thing I'd like you to note from this is, again, the energy transformation aspect, because we spent a couple chapters on energy during the semester. Make sure that you do remember the types of energy and how they transform between states. Yes?
Why wouldn't you take away friction? Isn't it like taking away from the final energy?
It is, you are right. The fact that energy is going into friction means that there will be less energy in the kinetic state. And in an interesting way, to do that right, you actually have to have a plus sign on the work done by friction.
Okay.
The reason for that being, if there was a negative sign here, say if you were solving for this velocity, you would then add it to the other side, and that would indirectly make velocity bigger. If there was a negative amount of work done by friction, that implies that friction's giving energy back. But here, with the positive sign, it is siphoning a positive amount of energy away into itself. And if we solve for velocity, we subtract it from the energy pool. Yeah, let me, looking back at the the exam proper, things I do want you to be able to look at this and take away from it are, one, again, remember how friction works. Two, be able to do energy transformations. Like in this particular case, mass 1, the hanging mass starts with GPE, and that's going to transform into KE as it lowers and the rest of the system moves. In the interest of full disclosure, the actual test didn't actually ask a question about the interaction of energy transformations and work not conserved by friction. So, let me check what other questions are on here real quick. Friction, energy.
There's another one with friction.
Yeah, I'm gonna go ahead and say that 11 is not the best, most representative question for the exam itself. I would say that number 10 is a better example of the sort of friction stuff that you need to be able to do and calculate, and then numbers 12 and 14 are better representative of the energy stuff you need to be able to do. Yes.
Sorry, for number 12, since we were like talking about it, I just had a question on where you got like the 40 from.
40.
In the 16 equals, V initial, or V1 final plus 40, V2 final. In the middle.
Oh, this?
Up, there.
Oh, there.
Yeah, I wanted to know where you got the 40. Because when I did, I just used like the 2 from the 2 kilograms, and I wasn't sure why.
Oh, what I did was, in an attempt to simplify this, I divided everything by 0.05. And the 2 divided by 0.05 is 40. So it was an attempt to cancel the 0.05 out. Note that
Okay.
from here to here, the 2 0.05s are gone. We've now got just 16 and just V1F. And there is no 0.05 to cancel here, so instead you have to actually divide it by 0.05, and the 40 is 2 over 0.05.
All right. Thank you.
Welcome. You could just keep it in the entire time. My brain looks for things to cancel sometimes. What else is on your minds and how you feeling? Well, I've got the practice exam up. I'm gonna quickly scan through it and try to point out some things that I definitely think are worth noting about it, and therefore things that I think you should definitely know and be able to do before the exam. Do you know how to calculate the weight of an object? And again, that is always on planet Earth, mass times negative 9.8. So if I ask you, how do you calculate the weight of an object? Your answer should always be m times lowercase g, or alternatively, big G m1 m2 divided by r squared, because that formula also technically works. Those are the only two ways to calculate weight. If I ask you how to calculate weight and or force of gravity, and you just write m, I will be sad. You do have to know Newton's laws. Remember from test 1, pretty much the only multiple choice question on there was, please identify Newton's laws out of these 5 statements. There's a new list of 5 statements. You have to pick out the rewritten laws out of that lineup and number them accordingly, and ignore the 2 statements that aren't laws of motion. the two not laws of motion statements. Might be true, but they aren't laws of motion. So you have to know the laws and be able to pick them out of a lineup by their correct number. On the practice test, it just asks you to write them, because again, the practice test is always meant to be more difficult and take more time, because we're ready to make the mistakes here. But just to quickly review, the first law is called the law of inertia. That's because an object's inertia is its innate property that tells it to keep doing whatever it is it's already doing. Object at rest stays at rest, an object in motion stays in motion, constant motion, until acted upon by an outside force. Inertia is the property of matter that tells it to do that, tells it to do whatever it's already doing until literally it is forced to do otherwise. So first law is inertia. Second law is F equals ma. Often we just shorten it to that equation, but if I was to read the equation out in words, that when an imbalanced force acts on a mass, that causes the mass to accelerate. And then lastly, the third law, for every action force, there's an equal and opposite reaction force. So if A acts on B, B acts back on A in the opposite direction. You do have to know the difference between centripetal force and centrifugal force. Note again, centrifugal force is the fake one that feels like it's pulling out of the circle. Centripetal force is the real one that pulls something towards the center of circular motion. So, know the difference. Fugal fake, pedal pretty real. Points to the center, I don't know. There's not, the mnemonic is better for fugal. 6 is about reviewing your first couple formulas. Number 2 is vector addition and also practicing basic trig and Pythagorean theorem. 8 is more trig practice as it relates to force addition. Projectile motion, if you throw something off of a cliff, be able to figure out how long it spends in the air, knowing that if it's a projectile, it automatically accelerates at negative 9.8 because of gravity, but only in the y-axis. And that its x motion is constant as long as it is only accelerating in the y. Again, for number 10, remember how friction works and be able to look at an incline and know how normal force, gravity, and friction are interacting on the slope. Number 11 is not the best example. I prefer you to look at 12 and 14 instead. 12 is collisions. I asked you to do both inelastic and elastic here. You do need to remember the difference and be able to work them both ways. 13 is an orbit question. Again, in space, gravity acts as a centripetal force. So the gravity between Earth and the satellite equals the centripetal force acting on the satellite, specifically on the satellite. So the satellite's mass is on both sides and cancels out. And the R is the same on both sides as well. So if R's are in the denominator, they will cancel out as well. Note again though, there's only one R here, there's an R squared here. So if that R cancels and the squared cancels, that leaves an R on the bottom. And if I ask you for orbital radius, that's what R is. R is orbital radius, distance from center of mass to center of mass. That's what the R is in both formulas, and if I ask for orbital radius, you're solving for R. 14 is energy transformations. Note again, there's many forms of energy and energy isn't destroyed. So as long as the world you're living in is temporarily frictionless, energy will convert directly from one form to the other. In this specific case, the spring cannon converts from EPE. There's kind of 3 stages to this one. Normally we consider a before and an after state, but in this one there's kind of a initial, partway, and then final state. The initial state is the spring is wound all the way up. Then after it launches, the EPE turns into KE, and then the final state is the object is as high up as it goes, GPE. So the 2 parts here are comparing different states to each other. First I compared state 1 to the final state, so wound up EPE to max height GPE. And then in the second part I compare the first state to the launch state, where the object is moving as fast as possible immediately after launch, factoring in that the object does raise up a tiny bit because the spring is pushing upwards. So note again, energy transformations, conservation of energy. how energy forms interact with each other throughout a process. 15 is several examples of rotational motion. Remember how those formulas work and interact back with their linear counterparts. 16 is a example of work and kinetic energy again, also rotational kinetic energy. 17 is power. 18 is torque, as is, there's a second torque question later on. 19 and 20, oh, my formatting got weird there. 19 and 20 are both waves stuff from the past week. 19 is wave speed, 20 is Doppler effect. 21 is the other torque question. 22 is pressure and buoyancy. It is technically easier to float in syrup, but I wouldn't recommend it. And 23, lastly, do remember what type of wave sound is. Longitudinal, mechanical. So it shakes like this, not like this, and because it requires a medium, unlike light. Mechanical means it requires a medium. Longitudinal means it is a pressure pulse in the same axis as travel. Light doesn't do that. So, you do the practice test, again, ignoring 11. I'm realizing now it's not the best representation of the exam. I think you'll be fine. And again, there's the content list on Brightspace that you should use as a sort of a study checklist. How you guys feel?
So we should skip 11 on the practice test then?
Yeah, I'd recommend it. There's other questions demonstrate the relevant principles better now that I'm thinking about it. And I don't like that there's two ways to work it to give different answers, so that's back to the drawing board for me. So, anything else on your mind for right now? Well, if that is the case, let's end lecture this year with something resembling a bang. You may have noticed that the standing wave rope and speaker has been replaced with this giant tube instead. That's not good. There we go. Now, this is still a standing wave generator, which is to say I'm going to use speakers and the same control boxes to make standing waves. There's a speaker installed in either end of this tube. However, I am not going to be making that standing wave on a string. I'm going to be making it with fire. Kind of an unfortunate part of Physics 1500 is, since we don't really talk about thermal energy, we don't really get to set anything on fire in here. So, let's do that. Right now, this cylinder is currently connected to the standard gas pump that is equipped in most lab tables at this school. And so it is currently being filled with flammable gas. And there is a bunch of holes sticking out the top of this thing. That gas is going to fill the tube and then come out through the holes in the top. It's filled enough. All right. Very faint fire right now, but I'm going to get every little spout lit, and then I'm going to hit the lights. So, right now, as the gas just fills the tube, it's going to rise up out through the holes and set on fire. So there's just a bunch of different holes right now. Note that the flames are all about the same size because the pressure within the tank is pushing all of the columns of fire out with equal force. But what I'm going to do now is turn on the wave generator. So take the speaker and physically activate it. That's 100 hertz sound, by the way. Note that that is a frequency within the range of human hearing. And the amplitude is so high, it put out the fire, which is rude. Now, The speaker that I just turned on is the one on this side. And that means that this speaker is the one currently making sound waves. Note that the columns of fire on this side are slightly higher, slightly more orange, than the columns on this side, until I turn the other speaker on. So now they are both blasting the same frequency into the tube from either end. Now this is 100 hertz, dang it, this is 100 hertz right now. And if you remember from lab and from when I was using the rope version of this last week, certain specific frequencies called harmonics would create different effects on the rope. A certain frequency would cause a second harmonic, which would be a full wave. A different frequency would cause like third and fourth harmonic. This right now is not any specific harmonic. This is just noise right now, pushing the gas out faster than normal. So now I'm going to tune it to second harmonic. And note, it takes the same shape as it does on the rope. One up, and then one down. Although there isn't really a down here, it's just both up. So this is a 2 crest second harmonic standing wave, same as the rope. Note again, 2 bigger columns of fire in relation to the shorter notes. And just to prove what frequency I'm on. So right now I've got this frequency coming in both sides. I apologize that the noise is going to get a little aggravating, so I'm going to adjust the amplitude. And now, if I double the frequency to 528, might be a little out of tune. Let's try 398.6 instead. There we go, third harmonic. Sorry again for the amplitude. The fact that there's 2 speakers makes it louder than normal. But you can do the same thing with fire and gas as you can with the string. And that's because, again, sound is a longitudinal pressure wave. The sound coming out of this speaker, since it's a pressure wave, it's going to force the gas into pockets of high pressure and low pressure. The high pressure pockets force gas and therefore fire out at higher volumes than the lower pressure areas, which come out less intense. So, actually, funny you mentioned Christmas. Right now I'm just playing pure tones through this thing. So again, what you're hearing is pure 396 hertz sound. Again, you don't usually hear pure tones in nature, so the pure whine is kind of aggravating in my opinion. But you can play music through this, in which case the fire will get more chaotic and bounce in time with the actual music. I'm pretty sure someone's built one and played Carol of the Bells through it. But you can do it not just 2-dimensionally, but 3-dimensionally. This object is called a Ruben's tube, kind of like a Reuben sandwich, spelled the same way. And if you look up Ruben's tubes on YouTube, or Ruben's boards, which is actually I guess this is 1-dimensional, a Ruben's board would be doing it in a flat plane. You can see people actually playing songs through these things, and the fire will dance with the music. I can't do music through this, but I can make the frequencies not quite agree, and that will create a beat. Which will cause a wave of fire. There we go. That's rippling. So, we set something on fire. Questions? All right. Well, that's about it for today. Huh? Well, I didn't build this thing. It has 2 aux cables, but I've never tried building it.
I got an aux cable.
Yes.
Wait. That's not an aux.
Sorry, it doesn't take aux. I'm sorry, guys. Look, I didn't build it. Let me guys know if you have any questions while studying. And please have a wonderful day. It's been great getting to teach you.